Introduction to Statistics, Chapter 6, Discrete Probability Distributions, Section 6.1, Discrete Random Variables. Discrete versus continuous random variables. A random variable is a numerical measure of the outcome of a probability experiment, so its value is determined by chance. Random variables are typically denoted using capital letters such as X. A discrete random variable has either a finite or countable number of values. This means the values may only consist of whole numbers, 0, 1, 2, 3, and so on. Some examples: the number of credit cards held by an individual, the number of siblings an individual has, the number of baskets made by an individual in a foul shooting contest. These all have to be represented by a whole number. The values of a discrete random variable can be plotted on a number line with spaces between each point. So we can have a number line 0 through 5 with a point at each one. A continuous random variable has infinitely many values. So this will include decimals and fractions. Some examples: the time required to swim 100 meters. You could measure this to the nearest second, nearest tenth of a second, hundredth of a second, so on. So there are many different possibilities, infinitely many. And the height of an individual could be measured to the nearest inch, nearest half inch, nearest quarter inch, and so on. The values of a continuous random variable can be plotted on a number line in an uninterrupted fashion. So you have 1 through 5 on a number line, and it's a solid line from 0 through 5. In each of the following, determine if the random variable is discrete or continuous and state the possible values for the random variable. Okay, think about these as we go through them. The amount of rain in Hagerstown during the month of April. Well, this would be continuous because we could, measure it to the 10th of an inch, 1/8 of an inch, whatever. So X is going to take on values greater than or equal to 0. Okay, the number of fish caught during a fish tournament. Okay, if we're talking about fish that are caught, this is going to be a whole number value, so it's discrete, and X can take on the value 0, 1, 2, 3, and so on. The number of customers arriving at a bank between noon and 1 p.m. Now we're talking customers, so again, this will be a whole number value. So it's discrete, and X would be 0, 1, 2, 3, and so on. The time required to download a file from the internet. Okay, in this case, downtime is, we could measure it to seconds, minutes, so this is continuous, and this could be anything greater than or equal to 0. So X would take on values greater than or equal to 0. So this is the difference between discrete and continuous. The probability distribution of a discrete random variable X provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or mathematical formula. Rules for a discrete probability distribution. Let P of X denote the probability that the random variable X equals X. Then, the sum of the probabilities equals 1. So the sum of P of X equals 1. The probability of each value is greater than or equal to 0 and less than or equal to 1. So the probability of each individual value has to be greater or equal to 0, less than or equal to 1. Okay, let's look at a few here. Decide if the following discrete variable distributions are probability distributions. If not, state a reason for not being a probability distribution. So if we look at number 1 here, look at it carefully. Would this be a probability distribution? And the answer would be no. Now, why would it not be a probability distribution? Well, the probability of 1 is less than 0. It's a negative 0.17. Okay, looking at the second distribution here. If we look at it, all probabilities are less than 1, less than or equal to 1, greater than or equal to 0. Okay, and if you add up all the probabilities, you would get 1. So this is a probability distribution. Number 3, if we look at this distribution, all the probabilities are greater than or equal to 0, less than or equal to 1. If we add up the probabilities, in this case, we do not get 1. So this is not a probability distribution. Now, graph of a probability distribution. We would have our vertical axis, horizontal axis. On the horizontal axis, you would put your random variable x values, 0 through 4. On the vertical axis, you put your probabilities. We can space these out because we're going from 0 to 1 for probability. Now, for x equals 0, the probability is 0.10, so we'd come up 0.10. 1 was 0.20, 2 was 0.40, 3 was 0.20, 4 was 0.10. So this is what the probability distribution graph would look like for this table. Now, we can also go back to what we talked earlier in earlier chapters: skewed left, skewed right, uniform, or symmetric. So in this case, this graph would describe as what? Well, if we look at it carefully, it would be symmetric. Now, the mean of a discrete random variable. The mean of a given discrete random variable is given by the formula. Mu of x equals the sum of x times p of x, where x is the value of the random variable and p of x is the probability of observing the value x. Interpretation of the mean of a discrete random variable. As the number of repetitions increases, the difference between the mean of the data, x bar mean, and the mean of the probability distribution, mu of x, gets closer to 0. So the more you do this, the closer the data set comes to the probability distribution. Let's say you roll a die 20 times and record your results and place your results into a probability distribution table. So first we rolled the die. This would be the raw data. These were our results. We got a 2, a 5, a 2, a 1, 5, etc. Now, if I found the mean of this raw data, x bar would be the sum of the x's divided by n. So if I add all those up, I get 65 divided by 20, and it's 3.25. Okay. Now, if I wanted to put this into a probability distribution table, well, the x values would be 1 through 6. That's the only thing you can get when you roll a die. So 1 through 6 would be your x values. Now, the frequency. Well, a 1 appeared twice, 2 appeared 7 times, 3 occurred twice, 4 occurred 4, 5 occurred 3, 6 occurred twice. So this is a frequency table, but I want a probability. So I would add another column for the probability of x. Now, if you recall from an earlier chapter, if I know the frequency and I know the total of the frequencies, the probability of x is the frequency divided by the total. So in each case, I would take 2 divided by 20, 0.10 for the probability of a 1. For a probability of a 2, 7 divided by 20, 0.35, and so on. Okay. Now, to find the mean of this probability distribution, I need to find x times p of x. So in this case, I'm going to take 1 times 0.1, 2 times 0.35, 3 times 0.10, and so on. And I get x times p of x. To find the mean, I would add this column. So if I add this column, I get 3.25. And you notice the mean from the raw data and the mean from the probability distribution table are exactly the same in this case. Now, the mean of a probability distribution may also be thought of as the expected value of, denoted E of x. So, if an 18-year-old takes out a 1-year term life insurance policy worth $10,000 for $300, and the probability the 18-year-old survives the year is 0.998937, which is a very high probability he's going to live the year, find the expected value of this policy to the insurance company if he dies in the first year. Let x be the amount earned by the insurance company. So, if we set up a table, we're going to have x, p of x. We're going to have survives, dies. Okay, if he survives, the insurance company is going to make $300. Okay. Now, if he dies, the insurance company is going to have to pay out the $10,000, but they already collected $300. So this is going to be $300 minus the $10,000, which is negative $9,700. So the probability he survives was the 0.998937. So the probability he dies will be 1 minus this. which is 0.001063. Okay. Now, remember how we find the mean, because the expected value is the same as the mean. So the mean is x times p of x, the sum of that column. So I take 300 times 0.998937, 299.6811. Take negative 9,700 times 0.001063, I get negative 10.3111. So to find the mean, or the expected value in this case, it would be, add those up, you get 289.37. So that's the expected value for that insurance policy. Now you have to realize the insurance company sells many of these insurance policies. So that is why, even though they pay out the $10,000, they still expect that to be 289.37. Standard deviation of a discrete random variable. The standard deviation of discrete random variable x is given by the formula. Sigma of x equals the square root of the sum of x minus mu of x quantity squared times p of x. Or there is an alternate. You could have sigma of x equals the square root of the sum of x squared times p of x minus mu of x squared, where x is the value of the random variable and mu of x is the mean of the random variable, and p of x is the probability of observing a value. Okay, so looking at an example, using a distribution table from rolling a die 50 times. Find the mean standard deviation. Well, first, I need to find p of x. So I take 5 divided by 50, 12 divided, 7 divided, all the way down. So now I have the probabilities. Next, I find x times p of x. So I take 1 times 0.10, 2 times 0.24, all the way down, fill in my x times p of x values. Next, I find the sum of that column. That's my mean. That's my mu of x, the mean for the probability distribution, 3.56. Now, if I want the standard deviation, I need to add another column where I take x minus mu of x quantity squared. So mu of x is 3.56. So I'm going to take 1 minus 3.56, square it, 2 minus 3.56, square it, etc. Now I need to take this times p of x. So I take that times p of x, and I get the following values. This is if you're doing it by hand, which you will not be doing by hand. And then we would end up with 2.5664 for that sum of that column. Now, to find sigma of x, we take the square root of that number. So the square root of 2.5664, 1.601998752. And that would be all if you're working it by hand. Now, using StatCrunch to complete a probability distribution. Click the icon and enter the frequency table into StatCrunch. Place cursor in a blank space and click Data on the top menu of the StatCrunch. Highlight Compute and choose Expression. Click Build at the end of the expression box. Under Columns, double-click Frequency to enter frequency in your expression. Click the division sign for division on the calculator. Under Functions, scroll down and double-click Sum to enter sum into your expression. Under Columns, double-click Frequency to enter frequency in parentheses for sum. Click OK, click Compute, and it'll put the data into your StatCrunch in a separate column. Okay, let's go through an example of this. Okay. So if I just stop this for a second, go down here to my example. Here is my example. Okay, the accompanied data represents the ideal number of children in a random sample of 900 adults. Complete parts A through D below. So here is my frequency distribution, and I want the probabilities of each of these. So I would open in StatCrunch. Now, here is my frequency table, but if you recall, we want a probability distribution. So we would go under Data, Compute, Expression. Now, you see the word expression here? We hit Build. Now, what do we do to get the probability? Wasn't it the frequency divided by the sum of all frequencies? So I'm going to hit frequency twice under columns. I'm going to hit division on the calculator. Under functions, I'm going to scroll down near the bottom where it says sum, double click sum, and you notice it comes up with parentheses. Double click frequency, that puts frequency. So this would be the frequency divided by the sum of the frequencies, which is our probability. Click OK down here at the bottom, click compute, and it automatically puts it into the table in a different column. Okay, so now you would just enter those values in. Let me go back. Okay, so let me slide this to the left, this to the right. Get back on this. Okay. Now, so the first one, it wants it to 3 decimal places. So it's going to be 0.01. The next one down is going to be to 3 decimal places, 0.032. The next one down is 0.572. For 3, it's 0.283. For 4, 0.081. For 5, 0.018. Now 19 when I round. And for 6, 0.002. Okay, so now I have those values entered. Okay, so I check my answer. Good, got them in. Now the next thing it wants to do, draw a probability, a graph of the probability distribution. Okay, so what we could do up here, we could go under stat. I like to do, because we're going to have to answer some other questions here about the mean and the standard deviation. So I'm going to go under calculators here. And I'm going to go down to custom, because we'll talk about this in a second. My X value will be my number of children. Now I got a choice. It doesn't matter whether I use frequency or the frequency, the probability. So I'll use probability. Click compute. Now you see a nice looking graph here. Well, this is the graph that we're looking for. We also see the mean and the standard deviation down here. So let's see. It's small, a little bigger. 2 is the largest, 3. So let me look at this. Well, 2 is not the largest here, so that throws A out. 2 is the largest. 2 is not. 2 is not. So just, looking at this, 2 has the largest. So that means it's going to have to be B, because B is the only one with 2 large. And if I look at the rest, they look pretty good. Okay. So then I check my answer. Did well. Now, compute and interpret the mean of the random variable X. Well, like I said earlier, the mean was right down here at the bottom. 2.4588, and it says to 1 decimal place. So 1 decimal place, that's going to be 2.5. Check answer. Okay. Now, which of the following interpretation of the mean is correct? Now, in this case, the observed ideal number of children will be equal to the mean ideal number of children for most adults. The observed ideal number of children will be less than the mean ideal number. If many adults were surveyed, one would expect the mean ideal number of the children to be the mean of the random variable. Okay. If any number of adults were surveyed. Okay. So this is going to be if many adults were surveyed. Then the mean is going to come close to the mean of the actual value. Compute the standard deviation. Well, if I look back over here to my StatCrunch, and it says 1 decimal place, so that's going to be 0. If I look right here, 0.8. Okay, so that takes us through that question. Okay, now if I go back to the PowerPoint, the next thing we want to talk about is finding the mean and standard deviation of the probability. Well, we already just did that. Okay, click the icon, enter the data into StatCrunch, click Stat on the top menu, StatCrunch, highlight Calculators and choose Custom, choose X for the values in, and weights would be P of X, and click Compute. Okay, so we just did all this already. So now, if we look at a problem, which I already did, similar to it, the mean standard deviation would be down here. This would be the graph. And now we could also compute probabilities by entering the inequality and entering a value, and click compute, and then over here we will see the probability of that individual one. So if we go back to our problems, not where I want it. Okay, problem 2. Now in this case, we're given a probability distribution. Okay, they want us to find the mean. So I clicked open in StatCrunch. Now, in this case, click Stat, Calculator, and go all the way down to the bottom, Custom. The values would be your X values. Your weights would be your probability. Click Compute. Okay, so there would be the mean and the standard deviation. So 3 decimal places. So it's 1.669, rounds up, so it's going to be 1.670. Check answer. Okay. Now they want the standard deviation. So I go back to my graph, and it was 1 point and 3 decimal, 1.229 it looks like. Check the answer. Okay. Now approximate the mean of the random variable X based on the simulation for 25 games. So now what they want you to do is go back to what we did in chapter 3. You click on the icon for the table. You notice you have a table for 25 and a table for 50. So they want the 25, so we open in StatCrunch. Now, if you recall, how do we find the mean standard deviation for a list of data? Go under Stat, Summary Stats, Column. Click on the column we want, variable 1. I want the mean and I want the standard deviation. Hold the Control key down, get them both at once. Compute. So round to 3 decimal places, so the mean is 1.44. Check answer, we're good. Now it also wanted the standard deviation, which I also had in my list, and the standard deviation was 1.121 because it wanted 3 decimal places, 1.121. Check the answer, and we're good. Okay, now it wanted me to do the same thing with the set of 50, which I just closed. So now I take the set of 50, open in StatCrunch. Do the same thing. Summary stats for the column, variable 1, I want the mean and I want the standard deviation. Compute. And let me try to put these side by side. Okay, and I'm down here. So the mean was 1.68. Check it. Yes. And the standard deviation was 1.151 when I rounded off. Okay. As the number of independent repetitions of the experiment increases, the difference between x bar and mu of x, the mean of the discrete random variable x, what should it approach? You do this enough times, it should approach 0. They should be the same. The mean of the x bar should equal mu of x. So the difference should be approaching 0. And what is this a property of? Well, we're doing it many, many times. This is the law of large numbers. And final check. Okay, so that basically brings us to the end of section 6.1.